Seeing as nobody's doing anything else right now, I thought it would be a good time to delve into the quantum speed limit. Just a little bit of fun numerology for those of us keeping track. You all know what that means. We conjecture ahead.
Although this is going to be weird, and it's going to be about a different.
Title of the conference was something like "Ground Truth" or "Turtles All the Way Down," and so it seems as though there's one Ruliad. I don't think it rules them all, and it might be just hyper turtles all the way down.
Yes, it's on the back of an infinite number of hyperrulial turtles.
Various people are commenting on the outrage of hacking the universe on a MacBook Air.
Alrighty then. What the heck are we talking about? Let's not bloviate. Alright. So, as I move myself into the correct position. There we go. I swear I know how to YouTube. Quantum speed limit. Okay, so we're going to... Link is in the doobly-doo. We're going to go with the Bremermann limit. What is this? Okay, again, Wikipedia. Take it for what it's worth. Go, check, verify, yada, yada. Okay, the quantum speed limit bounds establish an upper bound at which computation can be performed. Computational machinery is constructed out of physical matter that must follow quantum mechanics, and each operation, if it is to be unambiguous, must be a transition of the system from one state to an orthogonal state. Suppose the computational machinery is a physical system evolving under Hamiltonian that does not change with time. I feel like there should be an A there. Then, according to the Mangolis-Levitin theorem, I apologize. I want to say something Levi-Civita, but the number of operations per unit time, operations per unit time per unit energy is bounded above. Yeah, try saying that 3 times fast. Basically, it's 2 over h bar pi. All right, equals about 6 times 10 to the 33 inverse joule second. Okay, what should that mean? That's basically kind of an inverse proportionate to h bar, the elementary unit of action. AKA, when we turn on h bar, quantum mechanics happen. Something like that. Okay. Single quotation marks. That's how it's often said, but that's a different discussion. This establishes a strict upper limit on the number of calculations that can be performed by physical matter. The processing rate of all forms of computation cannot be higher than about the number we were talking about, operations per second per joule of energy. This is including classical computers, since even classical computers are still made of matter and follows quantum mechanics. Okay. Why am I talking about any of this? Because apparently this is a thing. Why? I learned it on Wolfram Alpha. You type in like speed or something like that, and it gives you those things, and it gives you the lower bound, which happens to be higher than the speed of light. And I remember I showed Professor Wolfram that, and he's like, "That's very interesting." And I feel like that may have prepared him for a talk he had with Jonathan about a year or so later, or maybe even this year, something like that, where he was talking about the upper limit. Oh, apparently this is the upper limit. I didn't really know it until more recently. I had to like look into it. But hey, these things happen. So why am I showing you this? Just, and again, take this for what it's worth. Perhaps this is just an interesting coinky dink. Okay, so you put in that. What was the formula? All right, 2 over h bar pi. Okay, you put that in. 2 over pi h bar. Okay, gives you basically the number they said there. It's basically, what is it? It's inverse angular momentum. So again, the inverse of h bar, but proportionally, you look at that and you're like, wait a second. There's a 2 and there's a pi there. Isn't the difference between Planck's constant and like the reduced Planck's constant like 2 pi, like a rotation? So you can shorthand it like this. It's just, I feel like this makes more sense to me. So we got a 4 and we divide it by Planck's constant. What are we doing? We're quartering a circle. Or we're circling a 4. Is that an inverse partition of a circle. We're quadranting a circle. Okay, this is getting more interesting the more I even think about this. Okay. Oh, don't worry. We'll go into the tangent too about other things. And again, we're going to have to follow the measurements. We're going to have to follow the science and see where it leads. It's like, again, could be right, could be wrong. We want to have experiments, scientific validation, because science is a process. It's not a person. All right. So we take that. It was per joule of energy. All right. So that must have been assuming 1 joule because it was 1. It's a hidden 1 in there. We often don't think about that, but it's things we should probably consider, and just an opinion. Okay. So what happens if we do the maximal energy? Well, that'll be the Planck energy. All right. That's the maximum quantized energy. All right. Cool. So we multiply by that. We get this number here. This ginormous 1.1 times 10 to the 43 per second, which, for those of you paying attention or looking right here, that's hertz. Because inverse seconds or inverse time, within the sciences, it's frequency. It's hertz. That's the unit we happen to use. I must have a ratio between the Planck frequency. That's interesting. What may that relationship be? First, we go to the Planck frequency. And how we define it currently, we have basically speed of light to the 5th over big G, the Newton gravitational constant, times h bar, the elementary unit of action. Now, that's all square rooted. It gives us 1.85 times 10 to the 43. All right. So let's divide those thingies. We got the Planck frequency, and then that frequency that popped out. Well, that seems like a manageable number. It's not like 10 to the 43. It's 1.571. And again, it's truncated because we have 5 digits going in, so we can only have so much there. We'll get into that. I may have jumped ahead a wee bit. Okay, so just cursory evaluation. We type those numbers into Wolfram Alpha. Oh, look. What seems to be fairly simple here. And again, it could be all these different things. But if we're just looking for a simple explanation, we have what? 1.571. That's not 1.571. Well, that's a 79. Entry-level approximation, you may round that up to 1. Seems like a pretty good, interesting thing. But I said Zeta in the thing. Okay. Now, I think Zeta might be here. Okay. I'm not completely baiting and switching you, because you actually need to delve deeper. Okay. Okay, we'll jump ahead to the end, or at least here. If it makes you feel better, I did it with some more significant digits. It seems to maybe be a potential deviation around the 7th significant digit. I'm sure that's totally another coinky dink. But what we get for potential closed forms? Well, the top two happen to be pi divided by 2. And to be fair, the square root of 3 zeta of 2 over 2, it is equivalent. So I really wasn't baiting and switching you or anything. They're equivalent there. You usually just don't see it because that's a little bit more complex. And you take a square root and stuff of that. We'll get to that in a moment. But okay. So we had our answer. We have our thingy there. We have our relationship. Okay, cool. Now, what happens if we square that number? So this is interesting. We get our interpretation. Vorticity advection. Because we're doing frequency, now this is frequency squared. What the heck is vorticity advection? Now this caught my attention because Rick DeWitt was giving his presentation on Archimedes' law of gravity. He mentioned that while he was going about a derivation, one could do a big G, you end up popping out frequency squared, or inverse. Basically, you get frequency squared. You get time to the -2. He happened to be using water as his mass unit there, which was very interesting. So what is vorticity advection? So Basically, yeah, and most everything you're gonna find is like on meteorology and then fluid dynamics, yada yada. It's derived from Navier-Stokes. So I just basically put in math vorticity. This seems to be a decent first level approximation. Again, standard Google AI, take it for what it's worth. Vorticity advection in mathematics refers to the transport of vorticity, a measure of local rotation. Okay, so something. Yeah, fill the tub up with water, you pull the drain. Oh, it starts to spin around. Apparently these little vortexes and stuff like that, they seem to be very useful. It seems to be difficult computations at a time, essentially describing how spinning motion of a fluid parcel moves with the flow. Mathematically represented by the dot product of the velocity vector and the vorticity gradient. And you go into our notation and everything. That's very interesting. Also interesting when you see the stuff. And shout out the fractal woman because she had, I believe it was Dr. or Professor John McCartney or somebody on. But he was actually talking about looking at things from a Compton wavelength perspective. So that got me to thinking. I kind of found this stuff a while ago and then didn't really think that much of it. I'm just like, I don't really know what to do with this. It seems like a fantastical result. To be fair, I didn't even notice the Zeta until just now. Because I went back, okay. I apologize. I'm bloviating. Okay, so I went to a more deep. Basically, I stripped off the units because Wolfram Alpha is still buggy when you do the squares with units right now. So you get this number here. And then this is what threw me off. It took me longer because I had to spend some time to look into this. I got this number. I'm scrolling down. I'm like, all right. Okay, so I got my, of course, you square it. You got pi over 2. You square that. What's it going to be? Pi squared over 4. You're just squaring both of them. Duh. Okay. What made me go on a side tangent was I'm like, all right, that's kind of cool. I'm just scrolling down real quick. I'm like, oh, the Zeta 2. And I'm like, okay, well, that's basically the same as that. So 0.4, 2.4. And then for those of you that may have been following some of the other videos or things put out there, I noticed this friend here. I'm like, wait. The square root of 6 Giesecke constants. Or we could simplify that as 3 volume complements of the hyperbolic figure 8 knot. That's interesting. Oh, yeah, and the volume of the Giesecke constant actually is the hyperbolic volume for an idealized tetrahedron. What the heck is that? Okay, it's something where its vertices technically would go to infinity. Okay. Kind of thought that. It's kind of been sated, seeing as you can construct a Giesecke manifold from an idealized tetrahedron. I'm going to assume the volume probably isn't going to change, but apparently it's used all the time for measuring hyperbolic space, just because it's a tetrahedron. That's a very interesting, just random thing there. So, and again, you can tessellate, measure things however you want. Some ways may be more useful than others, and you can get a little bit more simplistic. I'd say that's a good thing. Yeah. So basically, when I threw in some more digits for like H bar, yada yada, and again, this appears to be what it is. It appears to match the 1, 2, 3, 4, 5, 6. All right, so we got like 6 significant digits there. Deviates on the 7th. Should that be a surprise? I mean, the speed of light goes to like 9 digits. I didn't do it with all the other things, but that maybe that's not all that surprising. Why? I haven't delved further. Gonna have to save that for the week of the conference. Gonna have stuff and things to do. I have plenty of other things that I haven't been getting around to. But that's all I got. So hopefully, maybe somebody was entertained for this 15 minutes. Maybe in the temporal future, maybe this is absolutely nothing. Just the ranting and ravings of a crazy person on the internet. Well, whatever it may be, I guess the future we will see. Take care of yourselves, everyone. Peace out. It's a crazy world out there, but I think something really cool is coming. Just the opinion of a dude.